Motor Manufacturing Canada's Software Innovation Challenge. Just for some background, the TMMC, they have several factories for building vehicles. They're currently using AGVs, or the automated guided vehicles, to relocate and move, complex and intricate parts around a warehouse. Instead of having large assembly lines and conveyor belts, it turns out to be a lot easier to sort of work in a warehouse with these autonomous robots. So, our goal here is how we can efficiently automate this and speed up movement of these parts while maintaining the safety and consistency of the robots. The key metric that we have here is that 31% of warehouses actually use AGVs for part relocation. So think of a big warehouse like Amazon where they have lots of parts. They also use autonomous mobile robots to actually relocate parts within a warehouse. So the challenge that we're given, this is sort of the real world map of our challenge. We're given these TurtleBots, which is a robotics platform, and sort of the main goal is to move autonomously in this fashion here, where two robots are moving here. There's sort of dynamic obstacles running across the big diagonal. They've got drop-off sections. They even have stop signs. So each robot has stop sign detection with computer vision, and once it's detected, they should actually stop like a real car waiting for pedestrians to pass. So again, the robotics platform that we're given is the TurtleBot 4 using Raspberry Pi 4s running ROS2. The main sensors that we have, first of all is a camera, and we also have a 2D LiDAR. And on top of that, we also have an IMU just to get our sort of rotation in all three axes. This robotics platform is designed specifically for education and research, and it's supported by a large ROS community. So here's our cost. So again, here's our sort of overview of our safety. So our first task was actually creating a cost map. Here's a gazebo simulation of our current setup. I'll just pause the video here. This is our robot here. And this is the environment that you saw in the previous slide with all of the April tags. And what you're seeing here in the blue, this is the LiDAR sensor itself. This is representing each ray of lasers coming from the LiDAR. And once it sort of collides and bounces back from an object, the LiDAR sensor provides us the angle at which the ray was shot at and the range, or like the distance from the robot and the obstacle. So if you imagine, we can map where obstacles are using this technology. So as we're moving the robot around, we're using, actually just to highlight this as well, running it inside of a Dockerized container for ROS2, and we're using Python for all of our code. I'll move forward in the video. So as this is teleoperated at the moment, so I'm using my keyboard to actually move the robot around. But if you see here, we actually this is another simulation using RViz2. So on top of the gazebo simulation, let's see, like there's objects around here, sort of in this corner. And if you notice, we actually have that as well in the video where we're creating a map. So if I pause the video for a second, each of these red dots actually represent each of the LiDAR scans. And what we're doing is we're creating a cost map based on objects being scanned here, and we're creating a grid of where objects are detected. I'll go into more detail of what this means in a second. I just wanted to highlight that this is updating live as the robot moves. The LiDAR changes, and sort of we're looking at the robot sort of always moving, so the map moves around the robot in this simulation rather than us being fixed to the world in the gazebo simulator. So moving forward, our cost map node, it helps represent the cost, or sort of the difficulty to traverse an area of the map. How we accomplish this is by creating a 2D grid which represents visible obstacles. So if you imagine the entire sort of the square map that we're given, we represent each location of that map in a cell of a 2D grid represented in a 2D array. And The LiDAR sensor detects, of course, where the obstacles are, and each cell is then updated with a cost value, which represents the cell being occupied by an obstacle. So again, each marked cell is then inflated so that there's sort of a soft margin around objects so that it accounts for the robot's width and the size. So as it's turning corners, it knows where objects are. So this is sort of like perception and the awareness of the robot and where it is. Here's the sort of software architecture of our current cost map node. So if you noticed, the TMMC wrapper for the software environment, they're using a LiDAR node which publishes LiDAR information, their LiDAR scans, on the scan topic. And using ROS2's publisher and subscriber model, we've created a cost map node which subscribes to the scan topic. We then initialize a 2D grid for the entire map, and then we convert LiDAR scans into marked cells. What's important to note here is that the LiDAR gives coordinates in like polar form, where we're given a distance and an angle, and we can convert that using trig functions to sort of convert that into XY coordinates for which grid or which grid cell the obstacle is located in, which is how we're generating that sort of black and white occupancy grid. We then inflate the obstacles around it, which you saw by that gradient in the map, and then we publish that occupancy grid to the cost map topic, which is what actually the robot sees. So instead of using the LiDAR scans directly, we're using this cost map node to sort of represent all of the obstacles as a 2D grid. So moving on, I wanted to highlight the safety. So this is one of the constraints of the robot that we're given. One of the key challenges was whenever you're teleoperating the robot, or if the robot's moving autonomously, if obstacles are detected within a certain threshold, the robot has to stop and then move backwards. We found that the best way to overcome this was by sort of separating how we use the LiDAR scanner. We've determined, or one of our key assumptions is that the robot always moves forward when it's navigating around the map. As it's doing that, we isolated this sort of blue area, this blue range for the LiDAR scanner as the front and the sides of the robot. So if objects are within this blue area, which is within a radius of the robot, we consider an imminent obstacle being detected. And once that's detected, we first stop the robot. We then check if the path behind the robot is clear for it to move back away from the obstacle. If it's not clear within this 90-degree section behind the robot, we'll keep rotating until it is clear. Only if it's clear behind the robot will it then move backwards. This is sort of a design choice that we chose so that robots will never collide into objects in front or beside it. An alternate method of how we were thinking of this was, or sort of why we considered a different method, was to enable or to avoid moving backwards into objects. Because if you imagine sort of in the map, let's say here, if the robot is found in the corner and it sees one wall on the corner, we don't want the robot to back up into the other wall on the other side. So we sort of created this alternative method for safety. Let's say the robot's sort of traversing and there's a wall and it's coming in at an angle. Our first task is to actually rotate towards the obstacle so that we can move backwards away from it once it's perfectly lined up. So the pros for this is we're aware of its current heading and we take the safest direction away from the obstacle so that it doesn't move back into another wall if it's a corner. One problem with this though is we're concerned with time, and moving towards obstacles it sees is a big time loss, and we value speed. So we've avoided not using this alternative method for safety. Here's a couple other videos of how we've implemented safety. Let's actually turn down the volume here. Right. I'll show this video first. So in the simulation, we're using the same cost map to sort of visualize where objects are. And in this video on the side, The robot attempts to drive into the wall, but we're stopped by our safety node.
Just in case. This is a better.
So again, it drives into the wall, stops,
Wait, just in case.
and then
This
it
is a
moves
better,
backwards.
better movement.
So this is our safety node. And if you notice, it did not hit the other wall.
Let's hit that wall.
Alright. Moving forward, we also need a way to detect the stop signs. So if you noticed previously, there are stop signs across the map. The robot needs to be able to detect where stop signs are and then stop as if it were a real car. For the computer vision, we're using YOLO V8 as our stop sign detection. In the framework that we're given for this challenge, we're using the functions that we're given. We're provided the bounding box around a stop sign. So we're already given the model to detect where stop signs are. But the way that we're using this is that if the bounding box, which is represented by this green box, if the area of this box is within a set threshold, we consider the robot to be stopped, or the robot can actually see the stop sign. So we're using the bounding box's size to relate how far the robot is from the stop sign. Once it sees it, it'll of course wait for 3 seconds, and then we can resume all control of the robot. And in this video, we can demonstrate that.
Okay, I'll just hold forward. Okay, show the stop sign now. And it stopped. I'm still holding forward. And it should just go. Yeah.
Yeah, so in that video, it's teleoperated by me. If I move it forward and it detects a stop sign, it stops for 3 seconds.
Okay, I'll just.
Now for our autonomous control, our goal is to move forward at a certain heading. We're using a PID controller for both keeping a certain heading and also keeping a distance away from the left wall. So the way that we accomplish this is by using a PD controller to keep the yaw from the IMU on initialization. So let's say the robot starts facing forward. The robot can be moved slightly by different rotation of either tire on the left or the right side, and it can cause it to deviate from its original heading. And so we use a PD controller to minimize the error and keep that original heading as our master PD controller. In our inner control loop, we make sure that the robot is kept a certain distance from the left wall. This allows it to actually traverse the map without just staying straight. And every time it uses the April tags across the map to sort of tell it when to turn left, when to turn right, we use those April tags to sort of relocate the robot and tell it should be turning left at the moment. So once it turns left at an April tag, it reinitializes which heading it should be heading towards. And here's a video of that. So in this video, the TurtleBot is currently being autonomously controlled, so this is no longer being teleoperated.
Hey, it stopped. Hey. Now hit a wall. Oh.
So in the end there, we also demonstrated that on top of the autonomous control, it still stops for stop signs and still stops for objects that are being detected. Oops. Alright, so that's the end of our demonstration, but we do have some next steps. Our first idea for enhancing our navigation was environment mapping. If you saw previously, we had a cost map node, which of course creates a 2D grid of what the LiDAR can see at the current moment. Using sort of like, we can save its memory into like a global map. So on top of the local cost map, we can create a global map of where the objects have been located. And using mapping techniques, like there are mapping techniques out there like SLAM, but in our case, we're just using a 2D LiDAR. So creating a memory of its cost map on top of the IMU to locate itself or localize itself. We can create a map memory using the same grid system as the cost map. We can persist known obstacle locations during a single session. And on top of that, we can use the April tags as tools for the localization and calibration of the robot. Now, the benefit of this is, let's say the LiDAR stops working all of a sudden just within normal operation. The robot actually keeps a memory of where obstacles are, so it doesn't need to keep refreshing with the LiDAR sensor of where to go, because it already has seen where all of the obstacles are at. And on top of that, because we have turned the entire map into a 2D grid system with obstacles, we can actually use heuristic-based planners like A-star algorithms for efficient route generation. So instead of making the robot follow a specifically hard-coded path, the robot can actually autonomously go to set locations anywhere. And using a mapping technique like this doesn't have us restricted to a single map. So like this picture here, the robot will be able to work in any location. So you can move the robot from one warehouse to a different warehouse with a different floor plan, and you can use the same path planning method we have here. Another problem that we saw is for the stop sign interaction. We found that the stop signs actually collide with the TurtleBots because of the TurtleBot 4's height. The way that we sort of designed how we thought of handling this was by using intelligent stop sign handling. So upon detection, we have to halt and wait for 3 seconds, but using the robot's height data, we actually assess the risk of colliding with the sign's upper portion. How we do that is with the size of the bounding box of the stop sign's computer vision model, and if the robot is too close to the stop sign, we'll be able to turn around and maneuver away from it. So that's our smart evasion maneuvering. So after it stops, we use the LiDAR to detect the nearest wall nearby, and we'll turn away from the wall, assuming that the stop sign is attached to the wall, and it can navigate around the stop sign. And thank you for listening. That was our software challenge implementation, and hope you enjoyed.